Alright. Today I'm going to rewrite that even two in one print. Then when we call it, it will do again. I don't really have it. Okay.
Of the connectivity. What the control?
Yeah. So the last lecture is not there. It's not focused. Yeah, I just checked.
Not anything with that pin, red color one.
No. It's but from here, it's okay, right? Yeah. Then it on camera. I mean, like, it's focus. Yeah.
This is for.
No. Nobody wanted. Maths. I found his homework. He was missing his homework, but now this one. Oh, I have Ryan's. Check on it. Okay.
We decided for the second.
Midterm? Yeah, I was thinking,
On take home.
yeah, I was thinking. It will be take home because I want the class.
Okay.
So can I have the class on that day? You have it take home exam, but we will have the two class. Regular class, regular class, is that okay? Yeah. The take home. Take it home. Week long, 10 days before before the final exam. Right, so April 20th, or how about this, before due by April 31st. You know, be out by probably April 15th or so. I'll release it around April 15th, it's due by April 30th, but there is no 31st, right? If I make it due on 31st, you say there is no date, so you cannot. But you cannot. Huh? That they never came, so you never submitted. I was planning to do it. Ah, here. That's your homework. My error. Alright, thanks. Sorry. No worries.
But the final will be partial take home and. We take one class.
I haven't decided that yet. I did consider for a moment that I can take that class also, but that I'll get in trouble, I think. I think the university makes it very clear that you cannot have classes during final week. Because some students have 5 courses. And I don't know how they are organizing the time, and if I ask them to attend the class, get affected with that.
We won't tell them.
We won't have. I think that's what they tell you, I guess. No, you cannot even do. They really try to clarify that, yeah.
You can ask,
Yeah.
check what he does, because I think one time, or for the class I had with him last semester, it was at like 8 in the morning final,
Uh-huh.
and he doesn't like to wake up that early, I guess, so I think it was like a take home, but it was due like the Friday before finals or something.
Yeah, you can make it take home. Because then you're not hurting the student. But I cannot schedule anything, for example, a class. It's big no-no.
During final.
During finals, even I cannot make anything due
Yeah.
during the final week. That they don't spell it out very clearly, at least in our university. But there are universities which spell it out very clearly that beyond 5 o'clock on the last week of classes, nothing can be due. So they make it very strict, and in those ways it is also legal. In that sense, also can get in trouble for it. So I just follow that up, and even though I think only once or so, whenever that happened, I asked them to sign if I don't have any problems. But most probably, so the answer to your question is that it will be take home most probably, and I won't be having any classes in the final week, so it'll end on the Thursday of the final. I seems I'm going okay. I should be able to do things that I typically do. So we should be fine. Everything will get passed or picked up most probably. On that side, mess up like last week, last lecture I messed up. It should be okay. But even with that, I think it seems it's okay. I can manage. Again, I'm back.
That's for today.
Well, let's keep reading. Any other questions? Other than final exam and midterm exam? Is the course useful?
Mhm.
Going okay?
Okay. Yeah.
Okay. So. Oh, homework 9 is due today, right?
Yes.
So homework 10, the abstract homework, which has not been posted yet. Will be due next week, okay? April, today is 6, plus the 13, I suppose. Okay. So. This is all projected. I haven't posted it yet, but this one I hope to be able to post today. This is 11. I want to make a question related to what mistake I made last time. I didn't make a mistake. I was not able to finish. So just for my satisfaction, maybe that I'm clarifying. But homework 11. So we will have a homework every week from now on, I suppose, right? So that's the day of the exam. That's why I clarify that. And midterm 3, no, midterm 2, right? Midterm 2 is officially on April 20th, so but it's a take home. So no more April 20, so.
Would you give it to us on that day, or is it due that?
That's the bigger question. I have to
The day
make
before.
the exam. But I'll make the due date clear. How about that? I do know the due date, so we talk about it in a few minutes. We'll make it due April 30, whichever day it is. And available on. Hopefully. So yeah, that's available on. April 15th, let's say. Tentatively, if you allow me, I don't even know what questions to. I was thinking of a particle going like we have done constant uniform velocity, and I typically give that as a homework problem, but that will become an exam problem of what if something was going with very high speed, almost with speed of light. Like we talked about electric and magnetic fields, or we are talking about electric and magnetic field due to a charge moving uniformly. So it could also move very fast. And then how will its field look like? It's so,
It will be everything after the first midterm.
didn't understand.
It will be the subjects, everything after the first midterm.
Yeah, and since I'll be asking the question, doesn't matter really, right? I mean, so it'll constitute something of last 2 weeks probably. So that's a challenge again. I felt like I used to have take-home exams and what someone told me is that I think it was during the COVID period, they said that take-home really doesn't help because many students like to prepare for the exam and you're compiling things together. And I agree to that the whole thought process of compilation where you start thinking about what was taught in the first week to the last week, there is a learning experience there. And by giving a take home, I destroy that because you don't care for what was taught. Give me the question and I'll start thinking only about the question. Do you see what I'm trying to say? So that's when I started to make one question in the class and everything else is take home. Even if it is take home, I'll give one question which is very elementary, but that will make students work and prepare for it. And that does the job of organizing your thoughts about the course. And the question itself is just a token question where it's reasonably easy to score. It
I
doesn't
think
really-
it depends on who the student is, I guess, because some people prefer take-home tests because it's, I guess, less stressful than an exam environment.
I agree. So I agree to that. That's why I like take.
And also time constraints as well.
But then it is having this negative feature, which I pointed out. So to avoid that, make one question, let's say 5 points or 10 points out of 100. Which if they sacrifice, yeah, they lose it, but any serious student puts an effort into it and that helps kind of. So yeah, take home has a negative impact also. That's my point in a sense. Sorry, interpretation. Okay. Any other points? Okay, we were talking about a charge moving with uniform velocity and how the fields look like. That's how we would like to ask how for an observer, what is the electric and magnetic field looks like. And and for that, we started building the potentials and I got stuck at a point. I really wanted to use a trick. I did not want to substitute it. So it was bad on my part. And it was a reasonably straightforward thing, but I'll clarify that. So let's so a charge moving with uniform velocity. What we're talking about, and I don't know how I drew the diagram last time. So what we're having is this is a straight line. That's your z-axis. And that's my x-axis. Where is my y-axis? If that's my x and z, doesn't matter. Is it going in or out, or it doesn't matter?
It matters.
It matters, right? So x crossed with y has to be z, so y is coming out first. Right? So a positive charge, let's say, is moving with a velocity v, uniform velocity v, and that's your z direction. It will have an electric field if I am at rest. If I sit on the charge, it's very clear. Electric field will be radially outward and radially outward with respect to the charge, and the magnetic field will be zero, right? But we want to do this in a moving frame, so in a frame that is in which the charge is moving. So for that, we have the idea that magnetic field R of T is equal to the cross product of the vector potential and the electric potential the electric field is the gradient of a scalar potential. It also depends on time derivative of the vector potential. And the scalar potential we said satisfies your Green's, we said it satisfies the wave equation, right? So, and we knew the Green's function for that, so we said that's equal to Q over 4 pi epsilon naught. And dq r prime dp prime. So scan the whole space for the charge, scan the whole time, at what time the charges exist. And the Green's function is t minus t prime minus r prime over c divided by r times r prime. Right, that's your scalar potential, and the vector potential is pretty much the same. Yeah, I mean, I should also say what is the charge, and like when I say the charge, this is moving. The idea is that charge density, right? So r prime comma t prime is equal to q times delta of x prime, delta of y prime, and delta of z prime minus that's what charge density. And the current density we said is simply velocity multiplied with this. Right, so this is v, which is in the z direction, so that's k hat times v times rho of r prime. Right, that was the idea, and that allows us to write r or the vector potential pretty much just by multiplying this. This is a constant. So help me, what was this? So you need a, so this is mu naught. So it was just, I think, if I help me. So this is v over c. That's beta times 1 over c. So what do you want? I think that's correct.
Yeah.
So if I do this integral, I'm good. That's what we want to do. What is this? So there are two ways to proceed. We can actually integrate time first and scan the whole space, or we can do the integration over r prime first and then do the t prime. In this case, since there is all delta functions, we prefer to do the r prime first, but later on when we are doing radiation, it will be exactly the opposite. We will do the time integral, and that will be having more convenience. So let's do the integral over x prime, y prime, z prime, and we said that's equal to r t. So that's immediate in a sense. So q over 4 pi epsilon naught and scan in time. So that's an integral, and this is t minus t prime. I replace all the x prime to 0, y prime to 0, and z prime to vt prime. That's the same as saying this is x prime is 0, so it's x squared plus y squared plus z minus z prime, which is vt prime. So the denominator is x squared plus y squared That was, yeah. Yeah, scalar. Potential. We said that if you have a delta function, which. I think if you have already attempted on the homework. That you have that then you would see that if I'm doing a dt prime integral. And that is a delta function of, let's say, g. Of t prime. And if I'm evaluating that. Since we will be calling that f. And if I'm evaluating it at the integral t prime, then the general idea is that this is equal to find the roots of the function capital F. So find the roots of the capital F and then evaluate this function at those roots. And then take the derivative of the argument of the delta function with respect to t prime, evaluate it at t prime equal to the roots, and then take the magnitude also. In case that comes out to be plus or minus 1. And that place, I think your homework, if you have attempted on the homework, most, I think at least there are 2 or 3 problems which you have to evaluate some simple expressions on. If we do this for the function that we have there, we recognize that our function, the argument of the delta function is t minus t prime minus 1 over c square or 1 over c times x square plus y square plus c minus vt prime square. And that led us to finding the roots of this equation, and whenever there are the roots, we call that the recorded time or the roots, either way, or helps with either of the notation if you want, or terminology. And the roots itself we found satisfied. So this is I'm going to get from last week. And I just did this a moment ago. So I think I remember. So this is t minus v over c and z over c. And minus of x squared plus y squared 1 minus v squared over c squared plus z minus vp the whole square. Okay, is that what we had last time? Can we check on that if I'm mistake? This is exactly what we had last time. It's not that we made any error last time, it's just I didn't see through something. That's all. Okay. Oh, that's not what I had last time, is it? Just the lecture. The concern.
1 c square is missing in the denominator. I'm not sure.
Inside the square root, x squared plus y squared divided by c squared should be there, right?
What? Sorry. Divided by?
And here x squared plus y squared is divided by c squared. And also c minus vt squared also divided by c squared. But since you don't have that one in both, that should be multiplied, I guess, in left hand side.
Which expression are we talking about? This one?
Yeah, that one.
Dimensionally, that's the problem you're saying?
Yeah, inside that one, last week we got x squared plus y squared over c squared. Times the next term.
Denominator c squared is both like.
Is 1 minus v squared c squared?
No. 1 minus c squared is there. And x squared plus y squared divided by c squared is there in the last time. And also that is like denominator.
Oh, yeah, because dimensionally it is to be there, right? I see, yeah. This is what you mean.
Yes.
Correct, okay, yeah, that should be there, because otherwise dimensionally is wrong, right? This is distance, that's time. Otherwise dimensional, yeah. Thank you, okay. So this matters for a change. I thought, okay, again, that's a mistake. I got scanned. Okay. So we did, so this is where we were last time. Oh, we did a little bit more, because we need the derivative also, right? So let's do the derivative df by dt prime. And it is -1, so let me put the -1 here. So it is 1, and it's minus v over c times z minus v t prime divided by x squared the thing. If I take a magnitude, I just have to take the magnitude of this minus sign goes away, that's the point, and you have to evaluate it at t prime is equal to tr, that's another feature that's necessary. Okay, very good. So all this is a summary. And we have to use this to evaluate that quantity, that's where we were, and we said substitute, basically use this identity in that. So I will have my scalar potential to be equal to q over 4 pi epsilon naught. First of all, there is only one root. Notice there were two roots in principle, but then I said I'm interested in respecting causality. I would like the effects to come after the causes, so I dropped one root, right? So that's it. If you are anytime doing this and anything exotic or something new, if you really want to argue that actually things don't have to be causal, then you want to come back and put that back in. So if that is the case, there's only one root, so there is no summation here. I evaluate this quantity at t of r and then do this derivative, right? So the f of tr, this becomes just x squared plus y squared plus z minus vtr, the whole square, and then 1 over this quantity here, which is this piece 1 minus v over c, and no, v over c. This is a bit more, so it is z minus vt prime evaluated at tr actually. So this is all tr now. Tr divided by x squared plus y squared minus vtr, the whole square is square root. Bring this in, and this is equal to q over 4 pi epsilon naught. X squared, this is where we were. I mean, until this step, I think we went through fine. And minus of, that is this to cancel out, and whatever I have left is having the dimension of length, so it is z minus vtr. Okay, so now the idea was, the trick here is that I said we can recognize this easily from what we have here. Notice that this piece that shows up here is part of f of t itself. This piece here is part of f of t itself, but at t of r, at the retarded time. At the retarded time, f of t is 0. So this is nothing but T minus TR. So the trick is to recognize that x square plus y square plus z minus VTR square is equal to C times T minus TR. Right. So, and that's because, so this is using f of TR is equal to 0. Okay, I use that. That's what. If that is the case, then my scalar potential is Q over 4 pi epsilon naught. That's C times T minus TR minus of V over C Z minus VTR. That's not a very convenient or insightful expression. It's a trick to mathematically proceed, but in this form, it is not very insightful. It's correct expression, but it's not the best expression. So now we again go back. So you recognize this. So first this is what I missed recognizing last time. But once you have this, then you go back here. If f of TR is equal to 0, the TR itself has this as your equation. So recognize that using the root definition, I have x square plus y square times 1 minus v square over c square plus z minus vt square. That whole quantity is equal to, I'll take this on, so put that on the right side. So this is, so multiplied by c, so it is c times e minus v over c, z over c minus, right? So minus of 1 minus v square c square times t of r. And I've multiplied by c, so this is c here also. So that's the same as c times t minus tr. So that's taking these two terms. And I put, so I would like to write it in this form, right? So it is minus of v over c times z, right? And so I've taken care of this. And that is correct. Yeah, right. So I don't need to write this in this form. So v over c plus, and that is v over c. Whatever is remaining is minus v r. Right, that's hopefully this quantity. Where did that go? I'm getting confused. Yeah. So that's that quantity. So you have immediate expression, which is more insightful. Looks very similar to, in that case, like your charge, right? Point charge. But still, you have this 1 minus v square or c square floating around everywhere. That we will try to deal with now. That's plus z minus vt square. So if you're moving, that's your, remember, if you put velocity equal to 0, that means you're in the rest frame, you get back your electric potential, the standard electric potential, right? Set v equal to 0. And of course, you should get back. No doubt about that. But this is the corrections, and it goes in different places. But let's rewrite this in a form so that we understand this a little better. Okay. Any questions at this stage? This is what I wanted to end with last time here. But messed up. I will recognize this, the post. So that made next steps. Of course, you could have substituted TFR and got the same thing. That will be more tedious, a lot more tedious. Okay, but we want to process this a little, as I said. Remember, Lorentz transformation, right? How do we recognize this as a Lorentz transformation? Let me remind that gamma is 1/1 minus g squared over c squared. And beta is equal to b over c. And things are moving in the z direction. So that's 1/gamma squared, right? I'm going to bring that out. That's equal to, I can write this whole thing as gamma multiplying this whole piece. That's 4 pi epsilon naught. And that's 1/x squared plus y squared plus. So x squared and y squared is kept untouched. And then this is a in the denominator, so that's gamma times z minus let's say b over c, right? So it is beta times gamma times c times t whole square. Okay. If so, that's the way I want to see this form. If 5 is known, I also know A. A has simple feature, that's beta times k and the same phi, right? So it's beta, so it's a k hat times beta, and there is this gamma also there, and there is a 1/c of this. So I think so. So let me try to write this. Yeah, let me write this. So gamma times q over 4 pi epsilon naught. So 1/x squared. And there should be a factor of c. 1/c somewhere, 1/c. Okay. How does this work with our understanding of Lorentz transformation? This is expression for scalar and vector potential. Remember, what does Lorentz transformation do? We have x, y, z, and t. So that's your 4 vector. If you want, that goes to, so that's your 4 vector. That goes to x prime, y prime, z prime, and t prime in such a way that x is equal to x prime, y is equal to y prime, and z prime and ct prime is equal to gamma, beta gamma, and let me have minus here, and gamma, and z and ct. Particularly, if you want, notice that Z prime. So Z prime is equal to gamma times Z minus VT. Right, that's a transformation. And remember, this is gamma times V times CT, or simply as Z times Z minus VT. And if we were to put a T prime also, CT prime would be equal to minus beta gamma Z plus gamma times CT. That doesn't come so much, but still, that's what it is. What about scalar potential? This is a position, but we know that phi, I should have put the time, we have been putting the time first, right? T prime. Just so that zero component is in that way, so that's a scalar potential and that's your vector potential. But for dimensional reason, I need a C also, and this also will transform, right? So this transforms to phi prime over C and A prime. But remember, these are position dependent, so the components change and the positions also change. So where you would say that a x remains the same, ax is equal to ax prime, a y is equal to a y prime, and a z, so a z prime and phi over c, 1 over c prime is equal to gamma minus beta gamma minus beta gamma gamma times a z times 1 over c times phi. Okay. So that few things that we have to do if we want to find the scalar potential. So let's say if we want to find how R of t is related between the two frames, this is phi prime, R prime, t prime, right? There should be no confusion between the R prime, t primes that we used here, that those are integral variables. Now we are talking about two frames, right? This is one frame, that's another frame. These change, these transform, and this itself transforms. Phi goes to phi prime because it's the zeroth component of a 4 vector. So there are two transformations we have to do. What is A prime equal to? If we say that's the rest frame, in the rest frame of the particle, what is A prime equal to? Or what's the vector potential if I set on the charge?
0.
0, because V is 0, correct? So that's equal to 0. And why should I say that's that? Maybe I should say A is 0, right? Because what am I saying? C prime is the new variable, so this is A that is equal to 0, and this is what we are interested in, if you want. So our vector potential then is equal to, it will be gamma. First of all, there is a gamma because this doesn't contribute. So there is only this scalar potential, right? This goes to 0, so there is only a gamma over C. So I have to get a gamma over C multiplied by the scalar potential in the rest frame but I have to replace that. So this is a scalar potential in the rest frame. So let's say x prime square plus y prime square plus z prime square. But with the understanding that all the coordinates have to move now, right? So square root, this is a rest frame, and now I have to move x prime to x, or let's divide that as x prime, y prime, z prime. E prime has to go to x, y, z, and t, the Lorentz transform that. And that I know how to do. So x prime goes to x, y prime goes to y. So that stays the same. So it's gamma over c times 1 over 4 pi epsilon naught. And that's equal to x prime goes to x the same, y prime goes to y the same, and z prime goes, as we said, gamma times plus gamma times z minus vt and square it. And that's fine scalar potential in this, but except I lost the c. Where is my c? Where did I lose the c? Because when I was doing, there is a c on both sides, so there is no. This is a scalar potential, there's no c. Because there's a c on both sides. So we start by just saying that if you're on the rest frame, the vector potential is 0. So the scalar potential has only depends on the scalar potential on the rest frame, and we have to change the coordinates also. The simple idea is that fields transform as a vector. The potentials actually, scalar potential and vector potential transform like a vector, and the coordinates also transform like a vector. So first you do the vector field and your coordinates. That's the only thing we have to worry about. Do the same thing with vector potential.
Can you say if we are in rest frame, A prime is A?
Correct. Otherwise, it's more complicated. There is an A in here. But since we know the answer in the rest frame, this is the best thing to do. But the point I'm trying to highlight here is that this transforms separately, this transforms separately. There are two transformations involved. One is scalar and vector potentials is a 4 vector. The dependence, position, and time is also a 4 vector. Correct. So my point here is if I were to write it as a 4 vector, this is A alpha as a function of x alpha. This transforms. This also transforms. Unless it's a constant. If this is a constant, everywhere the same, which happens especially in electric and magnetic field, if it's constant everywhere, then it's convenient, then we don't want to worry about your dependence in here. But if whenever there is dependence, which is most often the case, two things you have to do. One is to transform the components of the potential and the dependence also. Okay, that's the message I'm trying to emphasize.
So here you make the like A0, like
That's just a choice because in the rest frame, A is 0.
otherwise we should have.
Otherwise, you'll have minus, yes, exactly, exactly. If you are in any other frame other than the rest frame, if you're comparing it with any other frame, then that whole thing comes up. Yes, you should,
Okay,
right?
so
And that's
it
it.
should be gamma 1 over 3 phi and that's another.
Then
one.
beta gamma, exactly.
No, I mean, if we take in the A is equal to 0, then it is gamma times 1 psi 1 over c, and there's another psi dash over c in the other side. That's why c cancels out, right?
Yes, C cancels out, yes.
Shouldn't that psi be the dash like prime? Psi prime is equal to that, right?
Phi prime, yes, so if you want, yes, yeah, it was phi prime if you want. Is this, okay, then this is our prime, right? Hold on.
Yeah.
What did I mess up?
You're
Because-
transforming, right?
Yeah,
Because prime is in the rest frame, right?
correct. So this is phi, yeah, okay, phi prime, I think some variables. If you want, yeah. So that all? Did I say this correct?
Mhm. Is a T also primary?
Yeah, that's what I'm confused now. Okay. This doesn't matter because even if I were to put this on the other side, this is 0, right? I will just make it plus. So this doesn't matter because A is Z 1 over C phi is equal to gamma, beta gamma, gamma times AZ prime and phi prime. And I used this to use that
Okay,
because I have this plus beta, right? So the next, when I write A, I'm writing a plus beta. So I'm actually using the inverse transformation. And here I'm using the opposite. Okay, so that's a good one. Okay. But however you do it, notice that you're, if I were to write it in this form, so how does A transform? A, let's say A prime, right? A alpha prime, X alpha prime is equal to, suppose there is a Lorentz transformation. Lorentz transformation of, so this is alpha and beta, and that is a beta there. So that's the Lorentz transformation in this. And you did this also. You have alpha now. So let's say lambda and gamma. Not gamma. Okay, so it's a delta, and this is X delta. Lorentz transform its fields and the position. In a most general case, L is complicated and it gets both.
and for the potential, there would be a charge, right? Q.
Oh, where did the charge go? Yes, of course. Sorry for that. Why did I not write it? You know? I did write everywhere else. Yeah. Okay. And of course, A is this, so that's the interpretation. That's good, that's scalar and vector potential, but we would be interested in electric field, right? Electric field is a lot more work. You have to take the cross product of this, correct? So let's do that. So now that we have the expression, let's put that down here. So it is, and now we have 5 or P on that to be equal to gamma, the Q over 4 pi epsilon naught, gamma over x squared plus y squared plus the gamma squared times v minus v squared. And A is equal to, let me cancel that out. And yes, so 1 over C K hat beta gamma times the same thing, Q over 4 pi epsilon naught. Right. And stick. We need to evaluate the time derivative, the gradient, and the curve. Right, few things to be done. Well, let's begin with time derivative, right? So time derivative is equal of A is equal to no time derivatives here. Only place where there's a time is this T here. So that makes it 1 over C J hat beta Q over 4 pi epsilon naught This is raised to power -1/2, so that is a -1/2. Coming in here, so the power changes to 3/2, so that x squared plus y squared plus gamma squared c minus p squared raised to 3/2. If we're talking in terms of electric field now, this contributes to electric field. So that's 3/2, and now I have to take the derivative of this. I will remember to write the gamma itself there. And so it is gamma cube apparently. So there's a gamma. I have to take the derivative of this. So there's a gamma cube and 2 times z minus vt. And take the derivative, so that's minus v. 2 cancels out, minus cancels out, so it is just v times c minus v. This is. So if you want, this is just beta, and I can get rid of the c. Oh, that's changing my mind, so that's v. Okay, I did it all up cut. What about the gradient of phi? Should be very similar. Except this time, when I'm taking the derivative 2 times z minus vt, I don't get this v, right? Minus v, I don't get that because I'm just taking the derivative with z, and it's only the k derivative, or actually that will be the x and y too, right? So let's write this. So 1, so this is pi now, right? So this is q over 4 pi epsilon naught. And gamma stays. Denominator goes to x squared plus y squared plus gamma squared, z minus vt squared, 3/2. And there's a -1/2 in here, but that always comes with a factor of 2x. So now here it is 2 times x in the I hat direction, derivative plus 2 times y in the j hat direction, plus in the z hat direction, so it is gamma squared z minus vt. The factor of 2 goes away, and there is a minus sign. So 2 factor goes away, and the whole thing is with a minus sign. But we are interested in negative gradient of this, so that would be having so the negative gradient will take away that piece in there. So what is the electric field? I just try to combine these two, right? So combining these two gives me my electric field, and that's equal to electric field of T algebra. Basically, otherwise it's mostly trivial. Negative gradient, so x and y is exactly this piece in here. So it is q over x 4 pi epsilon naught. And there is a factor of gamma. So let me write this in this form. So there's factor of gamma multiplied by x in the I hat direction, factor of gamma multiplying the y in the j hat direction, and z hat. Process that a little bit, and yeah,
Did you forget to write the k
Yeah.
hat in the numerator?
yeah. So this is k hat. Thank you. Thank you, thank you.
There will be a negative sign on dabba A or dabba T. There, because
Here,
no, the dabba A or dabba.
because when I hit the velocity sign here, there was a minus sign, right?
Oh,
So that minus sign went away there.
Okay.
Right, so here there is no minus sign apparently here. There is, so hopefully that will Can we do this together and go, come on? Okay. Okay, at least we can see the denominator having similar terms. Correct, electric field, I have to collect the negative of this, so hopefully all this works out and plus gamma squared z minus vt squared. I think that's clear. Okay. So with the negative sign, and this is with the negative sign. So now I have to process all this, right? So let's see. So in the k component is a tricky piece. So plus k component. And k component has this gamma q and z minus vt, right? So let me write the gamma there. So there is gamma squared z minus vt. And there is a gamma squared. That captures this piece. Right. That's my gradient of pi contribution. Basically, there is a gamma times z minus vt, and there is a gamma squared. I want exactly the same analogous piece from the minus of this. So there's a minus z minus vt I have taken care of. Gamma I have taken care of, and there is a v over c. And there is a beta, so there's a beta square, but that comes with a negative sign. So that's a beta square, gamma square, I suppose. Did I get everything correct? Okay. Okay. So. And the idea is that what is gamma square minus beta square gamma square? Straightforward. One, right? So that goes away, and that gives you the idea that this is q over 4 pi epsilon naught. So something is off here. I'll find a mistake if there is. Gamma x, gamma x in the I hat direction, gamma. I think so. Get out the gamma. Gamma x I hat plus y j hat plus z minus vt k hat, and that's divided by square plus y squared plus gamma. So this is a Lorentz contraction, if you want, of both z and t. Crucial. Like it's a difference z minus vt analogously that's contributing. Think it's okay. Yeah. But we need magnetic field also, right? Magnetic field somehow should be circling this charge, right? Where in the moving frame there should be a magnetic field around it. So that should come out from the curl. But curl is basically the same idea, except that if you have the gradient of A and gradient of phi is the same, right? Gradient of phi versus gradient of A, except I just have to have the K in it. Right. So when I'm taking the gradient of phi, that's here. So this is also, so I can, let me just write it out, right? So this is equal to gradient of A is pretty much the, without the operator, right? Cross product I will put in a few minutes. That's equal to minus q over 4 pi epsilon, but a comes with k. Right, so there's beta over c. Beta over c q over 4 pi epsilon naught. Gamma. And x I hat plus y j hat plus gamma square z minus vt k hat divided by x square plus y square plus gamma square c minus vp square 3 by 2. And that is a k hat that sits right in front of you. If I'm doing the cross product, or if I'm doing the curves, I would introduce a curve here. And that kills that k term. K crossed with k is 0. So then I took that, oh, that's not there. So basically, it is the same idea, except I have a beta over c in the problem. Yeah, that was the issue, right? You guys didn't stop. Was that a mu naught here somewhere? No, right? Oh, mu naught, I absorbed it into C. No, it's okay. So,
I don't think.
yeah, so it's all okay. So the C and epsilon somehow conspire to make it a mu naught. Yeah, magnetic field. Hopefully we'll see that. Okay, let's see. There's a mu naught that comes up. Okay, so that's equal to, I think all this goes through. And I have why the minus sign? Minus.
Which
Yeah.
one, the minus?
Oh, because I had crossed with k hat. I with k is how much? I
Minus
x
j.
and a z and it's j, is it?
Yeah.
Minus j.
Minus.
Yeah, so it's minus j. So then I have to say this is b beta over c q over, oh, I want to write this as, yeah, maybe that's the point. I want to write this as q times v, right? So this is 1 over c square, which is mu naught, right? So that makes it mu naught. Yeah, I see my mu naught now. And that is q times v. Right, that's a moving charge divided by 4 pi. And that is gamma. And we have minus x in the j direction, j hat direction, and plus y in the I hat. Divided by x square plus y square plus gamma square z minus vp square and divided by 2. If you remember, like rho, suppose I say rho is as a vector is equal to x times I hat plus y times j hat. This is a cylindrical coordinate, right? Then phi hat. So this is a cylindrical phi. Or rho hat would be. What it is. So rho hat would be x I hat plus y j hat over x squared plus y squared. And phi hat would be the perpendicular vector. So that's your rho hat. And that's your angle phi. And that's your phi hat. Perpendicular to rho on a circle. So another way of looking at it is that if you have a circle, that's my phi hat. Tangent vector to the circle, that's phi hat. That's equal to, if this is x and y, that's angle phi. So this becomes the y-x component is actually so what's going on? So this is y, that's your x. Opposite to phi is y. That's your opposite to phi. The adjacent is x. So the phi is given in terms of minus y. So. I got this wrong. Sign is wrong. Because there was an overall minus sign, correct?
Yeah.
Yeah, there was an overall minus sign here. Well, that helps. So this is equal to x minus y in the I hat direction plus x in the j hat direction divided by x squared plus y squared. Or you can say this is a cross product of the observation point and the source point, correct? So this is how do you say it? So v times so q. Another way to look at this is that q times v as a vector crossed with vector rho is equal to q times v, make it rho hat times phi hat. K with rho, right? K with rho is phi hat. Like that. So that's another way of looking at it. So then D is equal to or T is equal to mu naught over 4 pi times gamma of QV crossed with rho hat or vector rho divided by x squared. Two. One more in the last 2 minutes. Finish. How does this look like? Gamma, remember, is always greater than 1. Time dilates, right? Gamma is greater than 1. That's why time dilates, and 1 over gamma is less than 1. That's why length contracts. And if you have this charge that is moving in with velocity v, if it was if v was 0, then you will have circles, right? That's your circles, right? But now what is happening is that all the electric field is getting dilated in the perp directions. So that's your electric field in here. So it forms an ellipsoid in a sense, and that's your E here. So how you draw this typically is that that's your positive charge. Make it like this. And I'll explore this further in your homework, where I'll really compress this into things moving fast. And this is how the electric field looks like. And the magnetic field will go in this direction. It will get weaker and weaker. So as we go, will get weaker. So that's represented by same thing in this direction. We'll talk about that more later. I'll come back to that. Yes.
So electric field using contractors.
Yes, electric field. It's basically what is happening is that you put all, like if this is your field lines, they all hold up in the plane of the motion. Faster you go, more it is happening. And I'll emphasize that more. So effectively, yeah, that's what you want to keep in mind. that you're actually holding it up, but we'll come back to that.
And the magnetic field becomes smaller.
Magnetic field also gets, like in general, magnetic field is not there, right? So in any way, if there is a charge that is moving, the magnetic field lines are more closer to it and then farther. This is just that it is farther. Earlier, there was no magnetic field to begin with, right? Now it develops a magnetic field, but they're all curves. But they are getting weaker just because of standard 1/Q. That's the old phenomena, but now this shows up. And more faster you go, there will be more magnetic field. The magnetic field will keep increasing, and the good feature would be that as you go faster and faster, the electric and magnetic field will become perpendicular to each other. Right, and they will all be in a plane, and that's what I want to. That's not really very important as such, but it's a nice thing to observe and probably will form your part of your exam that is on. Usually I give it as a homework, which is supposed to be released today, but then I'll remove that and put it in the homework. And I want to keep something new in that, add on something to it, small piece to that, and do that as a, that's what I'll do.
So wait, as it gets back, as the V increases, the magnetic field is become perpendicular to the field.
No, magnetic field is or was not there to begin with, right? It was zero. If you're at rest, there is no magnetic field. The moment you move, there is magnetic field, which is the usual, it is curves. Like as the car moves, there is more and more magnetic field going around. But what changes is that typically magnetic field is there in the front and at the back.
Yep.
Right, so there is a bit of magnetic field in the front also of the charge, right? If there is a current carrying wire, there is magnetic field here also, right? That is how we do this. So there is its curls that are coming in here. But if I put this shorter, this still has an effect there. Like a small element of wire will have a magnetic field in that part also.
Yes.
But as you go faster and faster, all the magnetic field will come closer and closer. The effect is less and less in the front and back.
Thank you.
So the point is that the plane takes over as you go faster and faster. So the field gets folded up to a plane. And I'll bring that out in the extreme version of it approaching speed of light, and it will be confined on a plane in that case. Which is very unrealistic because nothing can go faster than as fast as light. But in that real sense of taking a limit, you're never going there, but you go closer and closer. This whole thing should become a delta function. Right? So the whole electric and magnetic field will be confined on a plane, which is described by the delta function. So that limit is very easy to take. If you arrange, this is a very overwhelming expression. Algebraically, it is not very clear how to see this. But if you write this in the correct form, that delta function comes out very nicely, which is kind of nice. So that will be your homework. Okay. Also, that will be your exam. Okay. Again. Yeah. So this folding up in the extreme sense.
It gets faster.
As it gets faster. Yeah.
Both magnetic and electric field.
Okay. Confined on a plane. It's kind of interesting if you think of it. So they think of two very fast particles, right? Like two charges. Let's say I'm going with speed of light, very close to speed of light, because I cannot go at speed of light because then I'll be massless. I am going extremely fast, and let's say Aryan is also going extremely fast, and we want to communicate with each other. Whatever signal he sends is all going perpendicular to the motion. So if I'm in front of him, it will be very difficult for him to communicate.
Yep.
All right.
Yep.
So very counterintuitive. Yeah. Okay, you say, how does two speed of light, two photons communicate? Can they communicate? Right. So that's all.
Quantum entanglement.
Yeah. how does entanglement talk, right? That's also a question. That was a big debate, but that was a paradox in a sense that if they are entangled, how do they communicate? Quantum mechanics has no information of relativity, remember. The quantum mechanics is non-relativistic by construction, but there is no speed of light. So how do they communicate? So, the instantaneous entanglements is instantaneous, but then when you bring in relativity, that becomes not causal, right? So that's how you create the paradox, and then you settle it all principles.
Spooky action of.
Yeah, exactly. That's why all those words begin appearing. Right, that's all. Okay, let's stop here. I have to attend a talk, and Manuka, you will help me. Oh, but I have to wind this up because I have to carry this to it. Oh, because we have a speaker from outside, so I have to run.
Quantum field theory this time.
Huh?
Today is about quantum field theory.
Quantum field theory, yeah, exactly. So I should take this. Can you reach him by any chance?
Come on.